probably go for about an hour and then switch to the case study.
Yeah. And the other thing is, several people asked for a participant list. On your USB, there's a USB drive. There's a folder called admin transport, and my sleep-deprived brain put the participants' emails, I think it's called PDF, in that admin transport folder.
Very
It
good.
is there somewhere.
Thanks, Jeff. Okay, so we're going to be just building on the model that we've built up. Okay, actually, I'm sorry. We're going to be actually using a different model. We will probably elaborate the model we've built up. But the purpose of this lecture is to expose you to interagent communication. Agents within AnyLogic traditionally evolve conceptually in parallel with each other. Each agent is going on and having things happen to it, having state transitions over time and so on, concurrently with the other agents. And the most popular means of communicating between two agents is with a technique known as messaging. And in this sort of situation, we make use of a means of communicating information between the two that is, as we say, asynchronous. So it doesn't require any sort of lockstep evolution of the agents. Instead, they can each be going on. One will notify the other by sending a message, much as someone might send you a text message. And you can check it when you're comfortable, when you're ready to do so, continue on, etc. The alternative to that is something more similar to a phone call, where they call you and you need to be there talking to them. That requires more coordination. A text message is a lighter weight thing. It allows communication between two parties without the assumption, indeed the presumption, that that message will be handled immediately. We're going to be talking about two ways of coupling agents. One is discrete with messaging, and there we're passing a packet of information. Another is continuous with stocks and flows. We're going to concentrate on the first of these. In this case, messages will be sent from one agent to another. It can include some payloads, some information that's passed along with the message. A given message can be broadcast to a set of agents or sent to one particular agent. Frequently, these messages are sent locally to neighbors in some sense, either over a network or in space. Okay. One of the most common ways for handling these messages is in the use of state charts. So we've seen two types of transitions that we've put into place. One is a transition where it's with a certain chance for you to become a hazard of transition that's independent of how long you've been in that state. And then we saw something that was quite different, which is a situation where your transition depends critically on how long you've been in the state, and you transition after exactly a certain amount of time. Well, another type of transition is triggered by a message, the arrival of a message, typically sent by another person or by the environment as a whole. This transition can then allow you to go to a different state, and it may also undertake actions. So for this this particular investigation, just to browse through it, I'd actually like you to open up a built-in example. So I'd like you to go to Example Models, and we're going to find this model called SIR agent based. So let me just see if I can. Oh, I should tell you, in AnyLogic, this is a tip, and it's actually very useful. This applies to Eclipse, the framework in which it's built. If you see a given tab in Eclipse, by double-clicking on the tab, you can make it. You can make it a full screen experience, so that will then occupy the entire screen. I double-clicked twice, I guess. So here's the full thing by double-clicking on this. If I double-click again, it retreats. So in this case, what I'm going to do is to call up the example models, and it will kind of put them down here at the, put them over here, I guess. Okay, well, okay, it's already full screen. Well, fair enough. And I'm going to go down to, and I have to be careful with this. I think it's under this, it's not under, it's under examples, I believe. And under, it may be directly here under healthcare. I guess it's under healthcare. They've shifted this around in different versions of AnyLogic. Excuse me, no, it's not there. I guess it is down in this how-to. Pardon me, I normally give an exact reference for this. So I guess it's in, yes, it's under how-to models, SIR agent-based. You have to be careful because there's several with similar names, SIR and GIS space. This is a SIR agent-based, okay? Some of you may already have it loaded. If so, you can just say yes, just get rid of all existing changes. So here we have SIR agent-based. We've seen this one before. This, in fact, is associated with simulation that we're doing earlier today with this spread of infection. Okay, this one here. So you'll recall that. If you have that open, I'd like to walk through the structure. Okay, so here we have agents infecting nearby people, and there's several components to that. The first is, how does someone get infected in the first place? Well, that occurs within the state chart. So if we go up to the state chart here, and we click on the transition from susceptible to infectious, we'll find that it's triggered by a message. So when a message comes in from anybody, it is sufficient to bring someone from a susceptible state to an infectious state. You'll notice it's unconditional. On the other hand, we could check if the message equals something, or we could do it if a certain expression is true. So, for example, if with a certain probability we could be infected, we'd put in an expression as true of, say, random true of such and such. We could do random true of 0.2, which would give a 20% chance each time a message arrived. Here we're going to be doing it unconditionally. Okay, so when a message arrives from presumably a neighbor, it will knock someone who is in, if they're in the susceptible state, it will knock them to the infectious state. Okay, does that make sense to people? People comfortable with that idea? That if this message comes in, now we'll see where this message comes from in just a moment. But if they're in a susceptible state, that message will knock them to the infective state. If they're in another state, the message won't matter at all. None of these other transitions are triggered by that message. So they have to be susceptible to get infected here. And that's how the infection occurs. That's when the message will make a difference. In all other cases, it falls upon stony ground. Does that make sense? Are people comfortable with that? Okay, so now let's go take a look at sending a message. Sending a message is done, in this case, when a person is infective, and that is infectious. So if we go to this state, you'll notice there's a self-transition. Now, one thing that may not be obvious is that the fact that this transition is occurring, it actually matters whether the transition goes from the state to itself within the state or outside of the state. These are two separate things. In this case, it actually re-enters the state, and it will recalculate the timing of outgoing transitions, for example. Here, it doesn't re-enter the state. Okay, here it just remains in that state. So if this is a timeout, it'll be the time from when it first entered the state. On the other hand, if we have this transition going out and in, this timeout will be reset. It would occur 10 say, days from when it came back in. Okay, here we have a recurrent transition. With a certain rate, this transition will fire. And you may be puzzled about this transition because the transition is from, it seems, the state to the state. It doesn't even leave the state. So what is the use of that transition? Well, the use is that it has an action associated with it. And this is a general principle in AnyLogic. We have these action handlers that do things when an event occurs. That's how things get done. events are the way the model drives things forward. Events are the sort of units of work to be done. Here, when this transition goes off, we're going to send an infection message to a random neighbor. Now this random underbar neighbor is one of a set of possibilities that can be provided. If you look at the send message, I just did control space there right after the right before the parentheses. You'll notice there's two modes. One, I can send a message, okay? Both of them share a message as the first argument, the first parameter. In other words, we're sending a message to somebody. In this case, we're sending it, in one case, we're sending it to an agent. In the case we're looking at here, we're sending it with a certain mode. And it says, specifies the message sending mode. And there's several of them, all random, etc. And they're listed in the AnyLogic help. One of them is this one random neighbor, and that very specifically means a neighbor in space, okay? So one of your neighbors within your so-called neighborhood. And that's either one of four neighbors, well, if you're in the middle of the space, one of four neighbors, or one of 8. There's two types of neighborhoods. One where you have the diagonals as well as the cardinal directions, other just the cardinal directions, okay? So that's in space. It turns out there'll be another one which is random underbar connected, which means, for example, well, for that one it means the neighbors in your network to whom you're connected. So we can send based on locality of space or spend on based on locality of network neighbors. So in this case, we're sending this message as denoted by this string. Now, ladies and gentlemen, I happen to think that we should use, so strings are problematic because we can misspell them. It's not guaranteed that we'll spell it consistently in different cases. And if we care about what, in this case, we don't care what the message says. This could say hello, and people would still get infected because there was an unconditional transition here. It didn't care what the content of that message is. But if you're testing if the message equals something, it's a little bit fragile to put in a quote like this, because we might test if it equals something with a lowercase I. So therefore, I advise to you, ladies and gentlemen, the use of enums. Enums, ladies and gentlemen, I tell you, enums. They're a good thing, but I'm not going to pain you with it again. I learned my lesson. So you can go back and as your comfort develops, use enums because they give a single unique name for each message, and there's no danger. If you misspell it, it'll immediately tell you because it knows the name has to be, like before we had names male and female. If we put male in lowercase, it would have said, I don't know what that is. It would force you to name it consistently. Here, if you call it infection with a capital I here, and then you handle it and you check if it equals with the lowercase I, it doesn't know. It doesn't know. You're trying to look at the same thing. So anyway, this is okay. It works. It's just fragile, but it's an okay thing. So here we're sending messages with a certain frequency. We're sending it with a frequency as specified by this. This again is similar to a first order delay, set of cyclical first order delays in a row. So we have a certain hazard rate associated with sending this message, a certain chance per unit time that's fixed in this case. So here we're going to have a certain chance per unit time of sending messages, and their messages are going to be sent off at Poisson arrivals, for whom that's a meaningful concept. In other words, they're going to be sending them off with a certain inter-arrival time, which is 1 over this thing. So if we have a rate of 0.01, the inter-arrival time, the mean time between messages would be 100, 1 over 0.01. So this rate, if we have a rate of 1, it means on average we send 1 per time unit. Sometimes, there may be some time units where we send 2, somewhere we send 0, but on average it would be 1 per time unit. So you're sending a message. Does that make sense to people? So here, the fact that we say random neighbor instead of naming a certain neighbor, we could put down a neighbor here. If we wanted to send a message to Jeff, I could put down Jeff, if it knew who Jeff was in this, in the AnyLogic model. and then we could send a message to Jeff specifically. Here we're saying random neighbor, and we're letting it pick which neighbor to send to with equal likelihood. Okay, so it's uniform probability. Does that make sense? Absolutely. So if we wanted to have it send to neighbors with differing probabilities, for example, if we wanted to have some information that would have, you know, my link to Jeff have a weight of 0.9, my link to you to have a weight of 0.05, and then I could send to each of you with that certain likelihood. Maybe that weight would be proportional to the amount of time I spend with each of you, relatively. In which case, I could have a little function that I would call off, a method I'd call off, and it would use a custom distribution, the empirical distribution. It would pull the appropriate index of the person. It would find that person, would do this dot get connected agent of whatever numbered agent it was that I pulled, and then it would return that person, and then we'd send a message to that particular person. This is just convenience, and it's in many cases it's useful. In very many cases. Great question. Okay, so we've seen sending a message, we've seen receiving a message, but we actually haven't seen all the pieces of receiving it yet. There's actually another piece as well. So to see that, ladies and gentlemen, I'd like you to go. To the to person. If you go to person, and you look under the agent properties, you'll notice it says forward message to state chart. So the idea here is that in general, our agents can have multiple state charts. So there might be a state chart for HIV, there might be a state chart for Hep C, there might be a state chart for TB. And we want to record these comorbidities for an agent and have them all progress. So maybe there's exposure to TB going on, exposure to Hep C, exposure to HIV, and we'd like each of those types of exposures to be sent to the appropriate state chart. We can either choose to send all messages to one state chart, or we could actually have a handler here. When a message is received, based on which message it is, send it to the appropriate state chart. In most cases, for most models you're going to be building up front, you can just forward it to a state chart. Just say, I want it to go to this state chart, and often it's the only state chart, and you're fine. Just be aware there's that extra flexibility to route the messages to different state charts based on their content. So, oh, I was exposed to TB, that goes to my TB state chart. Oh, I was exposed to Hep C, goes to my Hep C state chart. I was exposed to a social messaging, some sort of meme perhaps I was exposed to, that will go to my attitude state chart or what have you. So here, just be aware that by default it's set up to forward it, but you have a lot of flexibility on that account. Let's talk a little bit more about messages. So we've noted that they can be sent to explicitly specified agent or an implicit class of agents, and I list them here. They each have a sort of Java name associated with it. Normally we send with send, like doing here. Occasionally we'll do it with deliver. Deliver basically forces the other agent to handle it immediately, which is presumptuous, but sometimes what we want. We want it to immediately respond to that. Otherwise, it just queues up a message, just like you queue up text messages during the day and may check them after some obligation. Okay, when we send messages, we often send information with them. We want to pass some information. For example, we may want to pass information about the context under which the message was sent, where a certain contact occurred in space. We may want to send information about the nature of the preceding situation, what led up to that. Some information is automatically passed. For example, you can automatically get information on who sent the message to you. So, for example, who infected me. That's all automatically made available through AnyLogic. You can, however, pass additional information if you see fit. So, for example, a deer model, if we want to simulate rut to mating of deer and subsequent birth, we may want to have the mother after a mating event, remember who the father deer was, so that later the paternity of the deer can be reconstructed. Yeah. Yeah.
After you run a simulation,
Yeah.
is there any way of analyzing the sequence of messages that have been sent and through the course?
It's a great question. If you wish to, you can accumulate information on those. And some of the models I've provided have a mechanism of what I call history accumulation, where you sort of can accumulate history of arbitrary events. This is very significant, and I'll highlight it as a very important aspect of individual-based models, that you can actually record a biography, as it were, of what went on to this particular agent that's longitudinal in character, and can be compared to longitudinal data you may have from the external world. So, for example, if we have, I work in the STI area in Saskatchewan, so we work with gonorrhea and chlamydia, particularly in Hep C, HPV additionally. And in that area, we notice, particularly for the STIs, the classic bacterial STIs, so gonorrhea and chlamydia, there's a large proportion of the infections occur to a small subset of people. The so-called frequent flyers that come back to the STI clinic quite a lot. There's no doubt that there's other infections going on out there in the population, and we have the evidence to suggest that. But it's a very large preponderance, upwards of 50% probably, of infections are occurring to the same set of people. And if you could look at individual biographies, as it were, over time, you could then compare those against historic data you have on individuals and their number of exposures over time and the time between exposures. And it turns out that's really useful. That's not something you can do readily with an aggregate model, because with an aggregate model, you're given a set of cross-sectional depictions of the population. How many people are infected at this time or that time or that time. You don't know if they're the same people or different people. It's just a count of people. Here we can actually accumulate this information. AnyLogic does provide ways of accumulating automatically certain aspects of model state over time in the professional edition, and I think maybe the next lower edition within it. Otherwise, you can accumulate them on your own, and it's very straightforward to do, and I have some models that will illustrate that. So when I touch on model output, I'll see if I can touch on that issue. Okay. So it's a great question. There's no built-in way of sort of recording, just telling it record all messages, but it's very straightforward to do. Okay. So any other questions on this right now? Questions? Okay, so message payloads are valuable, and we'll send payloads often with many types. One thing I'll just note for anyone who's interested, if you go to person, at that place where it was on message received, you'll notice that if you have here some information, if you put in a snippet of Java code here, you'll notice that you have access to two variables. One is called MSG, received message. So that's a reference to the message. So maybe you passed an integer, or maybe you passed a string, like here, the infection string, or maybe you passed a pair that denoted a latitude and longitude. You could get reference that, but you'll notice you also have identity of the sender, okay, who sent the message to you. So, if you wanted to, and I'll just illustrate this now. You don't necessarily have to follow along, but I'm going to use, and this will be the first time you've probably seen this, I'm going to print out some information when this occurs. It's a little bit like what was being asked before. I could say, I'm going to put my name first. That's me. It's going to be turned into a string. That's sort of who I am. Was infected at time. These pluses mean concatenation. In other words, they'll put a bunch of these character strings together into one place, and then it will print it out. That's what the trace ln is. So I was infected at time. This is a call to a method called time that gets back the time. You could think of it as a function that returns the current time. By, who was I infected by? by sender. Okay, so what this is doing is it's calling a method that says, hey, go print the string. What is the string it's going to print? It's whatever my name is, appended to this string was infected by, or concatenated with the string was infected at time. This is going to be time, and then it's going to say by the sender. Okay? Now I'm going to actually run this. Okay? Here I'm printing it to the console, but this could be sent to a database, a similar sort of information, or printed out in a file. So here we have the infection starting to spread. You'll notice, there we go. So this is the message I put in there. So-and-so, this is me. This is who was infected. Person number 220,000 was infected at time by null. Okay, what is that going to mean? We'll get to that in a second. But from then on, they were infected by particular people. This person was infected by, guess who? Who do you think this person would be infected by? This second person. They'd be infected by the first person. So this person who was the index infective in the population, they then infected this person. So you could see them. That's the same person. That's the index infective here. They then infected this person here. Now, interestingly, that person then went on very quickly, or in pretty short order, to infect another person. But this original index case then went on to infect someone else. And here's the timings of all the infections. Okay, so here we have a kind of map over time of who infected who, and I put this out in a very informal way. I mean, if you want to export this, what you do is put tabs between them and then export it to a spreadsheet. Ladies and gentlemen, this is going to record the full transmission chains, the transmission sort of tree of who infected who over time. That's all contained here along with the timing of this. A nice synthetic data set, in fact. But why this initial one? Well, the infection has to start somewhere. And in this model, what happens, there's two ways we can commonly do this. One way is you come in and we could actually have some people start infective. So if we actually put a branch up here, we could have some people go to the susceptible as soon as they come in, some people go to the infective, and that would be a way of starting some people infective. But in this particular model, what we're doing instead is we are having main just send a arbitrarily chosen person a message. So if we go up to main and we go to, I think it's under general, yes, you'll notice that when main starts up, and this is another example of these handlers, events happen, code gets run. Transitions fire, code gets run. You come into a state, code gets run. You start the simulation, this code gets run. And what this says is, hey, environment, deliver to a random person this message infection. So here we have that initial index infective is actually getting infected not by a particular person, not by the hand of man, but by the main class as part of its startup, by the environment. And that's why it doesn't have a particular person, a sender associated with it. It's the null sender. It's not a particular person. It's not a particular agent. Does that make sense to people? So that's how we get the in first person. Now, what if I deleted that? Don't do this at home. But what if I deleted this? What do you think would happen? Ain't nothing going to happen, as they'd say in our southern neighbor. So here we run it. And interestingly, though, you'll notice it just says finished immediately. There's nothing to do. There's no primal event that kicks things off. No thing that has to be handled up front. This is an event-driven system. So it goes from event to event. Now sometimes, ladies and gentlemen, there's long times between those events. Sometimes those events are going on in very short order. This is what allows us in AnyLogic to create multi-scale simulations. Some things, like maybe my immunological response, need to be handled on a very quick basis. Some things, like changes to the policy of a hospital to handle HAIs, or changes to contact tracing methodology, those sort of things go on at a much slower scale. One might say a stately pace, sometimes deadly stately. And AnyLogic, by virtue of being event-driven, however much time occurs before the next event, it just hops to the next event, hops to the next event, hops to the next event. So here, if things have to go on thick and fast, it will handle that. If things have to go on not at all, or if things have to go on super with great time between them, with great stasis, it'll go forward very quickly often. So that there can be sort of a punctuated equilibrium, and it will handle it just fine. Long periods of stasis, sudden actions, sudden breakdowns, say within a dementia ward for the activity in the dementia ward, and then there'll be long periods where very little's going on. This sort of modeling in a discrete events sense can end up really taking advantage of that. It doesn't need to do a lot of work for the long periods between it. It's just going event to event to event. What are those events? They include things like state chart transitions. They include things like sending messages. They include things like the startup of the model. It's going event to event to event. Now, the interesting thing is this may allow you some time to see puzzling things. So if I go here and I look at model time, ladies and gentlemen, it says time infinity. It knows there ain't nothing to do because there's no primal thing going on, nothing to kick anything off. If there's no events to handle, it's game over. It's only with an event that something would change to kick something more off. It's only while there's events in the queue that you're actually going to need to go forward. So here we have this underlying event queue to get handled, and once we're through that, as far as it's concerned, it can be time infinity because there's nothing more to do. Let me put it this way, to put it more intuitively. With an entirely susceptible population, there's no risk something's going to happen in this model, and therefore it doesn't have to handle that. Okay, so that's an illustration of this principle. Now I'm going to put this bit of code back for kicking it off. Okay. So does that make sense to people? Okay. So that was state charts. Let's talk about this a little bit. So sending this message, will right. So, well, I think I'll skip that. Here we are sending a string, and that's fine. We can handle, if we want to handle a message explicitly, so if we had a Hep C HIV model, we wanted to have them each go to its own state chart, we could have something like and I'll just illustrate this here. We could have something along the lines of, and it would be in person, because it's person who has to do the handling, under the agent properties, because it's agents that get message. And if we have on message received, I could say if MSG equals HIV exposure, then, or HIV infection or what have you, then I could say, HIV state chart dot receive message. I think that's the name of it. Yes, dot receive message MSG. So there I'm saying, I'm just delegating, I'm saying if this is an HIV related message, I'll just send it to the HIV state chart. Otherwise, I'll send it to the, the Hep C, HCV state chart, and so here probably I'm going to go afoul of Java's naming convention. So that's probably how I name them. So here, based on the nature of the message, we pass it to the appropriate state chart. Does that make sense? So this message comes in called MSG. I say, okay, what does this message say? What type of message is it? In this case, I say I encode it as a string, although I think that's bad practice. If I encode it as a string, okay, if it's an HIV one, I give it to the HIV state chart. Otherwise, I give it to the Hep C, and then the state chart takes care of it. The state chart will figure out if there's a transition that will fire, etc. So this is how it goes on right now. The fact that this is checked right now means implicitly what's going on is that if I don't override it, there's something like state chart dot receive message going on. This is kind of implicitly what's happening right now, just passing it automatically to the state chart. Okay. So those are some comments there. So that's receiving message. Okay. Any questions about that until we'll add it into our model, or to a model you can load in. Question? Yes.
When you have states or conditions within the that will allow you to send a message. For
Yes.
example,
Yeah.
you are implementing a policy A in a hospital B, but for that to happen, you need the team will be maximum 3 people to make it happen. So that team can take a month
To form.
to develop.
Okay. Okay. So I think what you're saying is, could you make the sending of a message contingent upon some condition, some situation? And the answer is yes. It's a great question, Roberto. And if I go to person here, and we go to this thing that sends the message. So in other words, I don't. If I want to think about a situation where the actions, I start undertaking actions once a certain condition is in place, I could put in what's called a guard here. Okay, this guard will encode the conditions under which this thing will fire. If the guard's not true, it's not going to go off. Okay, so you could put in a guard that would basically say the team is of sufficient number, the team is adequate in some way, in which case then it will fire, otherwise it won't. Does that make sense? Okay. Question? Yes.
So we reuse the sending message in the same way. So if we want to send from main to the state chart, is it the same rule?
Help me understand your question here. So if we want to send a message from main to a person, as far as main is concerned, it's sending to a person. The internal logic of a person routes it to one state chart or another using this sort of thing or with this manual message. Right. So in main, when we looked at this sort of thing, it just delivers. It actually delegates the job to the environment. It says, hey, environment, go deliver to someone in your population. Go deliver a message in faction. And then that sends it to the person. Then the person gets this message, and if they want, they could send it to different state charts. But by default, they just pass it to the first state chart. That's the one that's checked there, and it goes to the state chart. Does that make sense?
Yeah.
Okay. Okay. Other. Yeah.
Can we attach a number or variable to the message?
Oh yeah. Yeah. Sure. So to be clear about this, let's suppose I wanted to do this. It would be nice to think of a nice thing to send, but I could send what sort of information. If I had some heterogeneity, maybe I'd send my income or whatever. But I could send I could send my education level as the message payload. I could, this string that was there. This string that was there. That's just one arbitrary payload. I could send a random number. I could send, my current age. I could send my ID. So I think what you're saying is, could I send sort of some indication of message type on the one hand, together with some additional information? Yeah. So in that case, what I'd do is I'd wrap them up together. So I would send a pair, which is relatively easy to do with Java, or I'd send a thing called an array of 2 elements. So I could do send. An array of 2 elements. It'll be a new object array. I mean, this is getting kind of advanced, but I could do this, and I could say send infection, and some, you know, my current age or something like that, or my current my current educational level or something like that. Okay, and sorry, this would be something like that, and then it would send a send a message to that person. Does that make sense? Okay. So yeah, we could. It's readily done. It requires slightly more work, as you saw there. Okay. Other questions? These are great questions. Great questions. Yes. Yeah. Okay. Oh, huh? Right. So I think what you're saying is, let's suppose that you have a state chart which represents sort of the general situation, but some of those states are, your ability to go to some of those states is contingent on certain things being the case. Maybe it's an aspect of the current situation, something that changes over time, or maybe it's an aspect of your other characteristics, like maybe there's a state representing pregnancy, and it doesn't apply to a male, but it does apply to a female. So, yeah, you could readily do those with guards. You could also do it by setting the, I mean, in general, for AnyLogic, there's many ways to do these sort of things. Another way you could do it is set, well, this isn't a good example because we have it contingent on message. But if we go back to our model that we were building up, you know, we could have this transition. Okay, so this might be obviously this is it's not simulating spread of infection right now, so you have to take this with a grain of salt. Maybe it's like picking it up from the environment. But what you could do is, you could have a parameter. Let's say, is vaccinated, okay, and this transition here would be guarded by is vaccinated. This exclamation point means it's the logical not of it. So if this guard is true, then you can transition. If this guard is false, you can't transition. So here, if is vaccinated is true, it means you're vaccinated. So the guard is not of that, the logical negation of that, which means it's false. So the guard will be false, and therefore it can't transition in that way. So here it's contingent upon the transition. The other thing you could do would be to do something like have a variable. You have to be a little bit careful with this. I'm showing this. I'd have to double check the ordering of things. But this variable could be, infection hazard or something like that. And, it could be, if is vaccinated is true, it could be 0. Otherwise, it could be 0.01. And then we make the rate here just depend on this infection hazard. So in other words, this guy is 0 if you're vaccinated, in which case you can't transition. Otherwise, it has a sort of default value, in which case here this rate would essentially be disabled because when you're vaccinated, for those who are vaccinated, because it's a rate of 0. Does that make sense? Yeah, okay. Great question. Great question. Other questions? I love these questions because, yeah. Sorry? Yeah. Control Z. Control Z is one of my best friends in AnyLogic. Yeah. So Control Z will quickly. Yeah. Unfortunately, there's no undo button for the world yet. But there is an undo button for AnyLogic, and it's a major. It's a very valuable feature. Yeah. It's also good to practice to just save away a model that's working as one version before you start adding to another version. Save away successive versions so you can go back and if you find a bug, see if it was in an earlier version you used to produce results. If you submit for a paper, save away that version and keep it separate and do not modify it, etc. Okay, so other questions? Okay, so moving right along, we're going to add a bit of this functionality of spread of infection into this model. So here, if we want to have infection spread, now be spread among people, what do we have to do? You can tell me. We've just seen how that other model worked. What do we have to do to add infection spread to our model? For those who would like to avoid building on an earlier model, you can load in this model minimalist network ABM model. Okay, if you did that before and you're comfortable and it's working, just you can keep on going. Okay, but you could fall back to this. This is one of the example models we provided to you on the stick. Maybe they call it a thumb drive. Maybe they call it a flash drive. Okay. Okay. So what do we have to do here to add in messages? Pop quiz. So I want this person's transition from susceptible to infected to depend on getting infected from a person, not just on some fixed hazard rate, 0.01. What do I have to do? Sorry? Okay, good. So this transition, a good place to start is this has to be transitioned by a message, right? Okay, we're going to just do it unconditionally because we'll only have one message in our model. So we don't have to futz with what type of message it is, which actually will, if there's only one type of message and we start checking whether it's equal to this, it does give us a little bit of flexibility going forward, but it could also lead to risk of we're inconsistent in some way. Okay, so that's start one. Will that work? If I run the model now, will the infection spread? Why not? What else do I have to do? Sending messages. Okay, so how do I send a message? How would I modify this diagram so I'm sending message? So I'm spreading the infection. I'm transmitting it. What do? Oh, okay. So what do I have to add to it? I have to add a transition. Okay, where do I add a transition? Inside infective. Okay, it has to go. And does it go to another state or just stays within infective? Because I'm not changing states. I'm just doing something every so often, right? Okay, and let's suppose that I want to send a message on average every 1 time unit, and we'll call it infection transmission. Okay, infection transmission. That will be the name of this message. Okay, so this is a rate. We could set it as a timeout, in which case it will do it every 1 time unit on the hour and to the minute. But here we'll send it with a rate, an average of 1 every time unit. Okay, will it run now? So if we run this, what will happen? Anyone? So if we run this, will we see a spread of infection? Oh, sorry, I ran the wrong model. Sorry. I meant to do this one. So if I run this, will I see a spread of infection? Why not? Good. 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 Okay, so somebody needs to infect the first person, right? So we've talked about 2 ways of infecting the first person. You saw one in the other message. So here we could just have main go to, so environment dot send. Well, gosh, what was it called? It was called. I don't even remember. It was called. This is one I rarely do. So what is it called? It's called send message to random or something. Deliver to random, I think it is. That sounds right. Deliver to random. There we go. and I deliver a message. It could be whatever, infection. Now would it work? Maybe. There's actually one other thing we have to check just to be sure. Just make sure it's routing it to the right state chart. So forward message to infection state chart. Okay, we're golden. We're in good shape. We're in good shape because let's recap. We made this transition triggered by a message, so that allows someone to be infected. For an infective to transmit, we added this transition going off 1 per time unit, and go there. And then we got an initial person infected by main, the so-called startup code for main. We called environment.deliver to random, and we sent some message. It actually doesn't really matter what its name was. Does that make sense? Okay. Yes. It actually sends it to anyone, because that's the initial, that's the primal message. That's the very first message. And it's actually, while the whole thing is being started up, that's why it's main. So it's not being sent by somebody, so there's no real notion of nearness. It's just being sent to an arbitrary person in the environment here. Does that make sense? And it's just saying, hey, pick people with equal likelihood. Now, that's not a mechanism I actually use a lot. Why? Because normally I don't think people have an equal likelihood of being initially infected. However, it is working. Here we have an infective here. Looks like they are not, they just recovered and they didn't infect anyone. Let's try running that again. Maybe it was by luck of the draw. Well, we have. Sorry. Oh, thank you. Thank you. Yes. Okay. I wish I could say that was all part of the lesson. But we have this message going off here, and what's missing? So this message is going off. This says infection transmission. That's an aspiration. That's an aspirational goal. Infection transmission. We have to do something. Well, I could tell a story about it, but we won't go into that. This is infection transmission. We have to do something. What do we have to do here? There has to be some action we undertake. What is that action? We have to send a message. So we have to send infection, exclamation point, to, say, a random connected, okay? You can look up what these constants are in the AnyLogic help. So now we have this, now it's complaining. See, it says build completed with errors. So here we go, random connected. Oh, I spelled it with 3 N's. Okay. Let's go back to that. Okay. It should be with 2 N's. Random connected. Oh, let me put this up on the screen. Sorry, folks. Okay. There we go. Random connected. So that's in the action for that infection transmission event. That's going off periodically, on average with 1 time unit between firings, and it sends an infection message to a random connected person, one of your neighbors. Does that make sense? That's needed. Otherwise, it's just a name. Just an event going off doing nothing. Full of sound and fury, signifying nothing. But this is actually now sending a message every time it goes off to a neighbor. Now, that neighbor may not be in a susceptible state, but if they are, then they'll get infected. Does that make sense? No, I just was adding a bit of drama to it, but in this case, it doesn't pay attention. Why do I know that? I know that because here it just goes unconditionally. So it doesn't matter what it receives. It could be hello, it could be good day, and it won't. It will still fire. So right now it doesn't matter at all. It is good practice to, if you're going to name things with with messages, it's a good practice to stick to a convention. And some people like the exclamation point at the end because it connotes some big action that's going to occur. So they will reliably end it with exclamation point. But in this case, it was not terribly significant. I think I just tried to name them consistently. So if it had exclamation point one place, it would have it in the other. But other questions? Yes. Sorry. Oh, the startup code? Sure. So this was the code in the infection transmission. And you want the startup code. Okay. And this guy here is the startup code. So startup code in main. And there you go. Yeah. And it has to be in main because that's where the environment lives. The environment lives in main. Oh, okay. Yeah. Other questions? Yes. 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 No, it'd be discarded. No, to be clear, I mean, that's the default semantics. If you wanted to, you could save up recent messages and persist them for a certain amount of time. And when you come into the state, you could kind of ask, hey, are there any recent infection messages sitting around? But right now, they're instantaneous things. And they come on an exact time. They get handled. It checks, hey, am I in a state which needs this? Is this message going to trigger anything, in short, given my current situation? If not, done. I'm done processing that event on to the next. Does that make sense? Yeah. This whole, it's very much going in a mechanical way, sort of among these different events. One thing to realize is that events can be descheduled. So like, actually, when you come into a state chart, to a state of a state chart, it calculates all the rates for all the outgoing transitions, for example. But only one of them will actually take place. And when that takes place, it deschedules all the others and says, okay, those are no longer relevant. So it actually schedules things ahead of time and deschedules them accordingly. Okay, I'm going to build. I'm actually building with a button now, or I could build with this. Building will check if it is having trouble understanding your model. Just because it understands your model and it can run doesn't mean it's right. But if it's not understanding your model, you got to fix something to even run. Okay, so I'm going to run now. Should this work now? Okay, here's our infected. Oh, it spread, but it's in a kind of isolated subcomponent, eh? It's isolated, so there's only so far it can spread. Let's do something just a tiny bit interesting here. Let's go when we click on a person, let's be able to infect that person. Would you like to see that? What do you think? Okay, let's see that. So what's the representation of a person? I click on something. What am I clicking on? A circle. You click on the circle. So if I'm going to have it respond to it, I look to the circle to do it. That's the object I'm clicking on, okay? So I'm going to go to the circle here. And now we're going to have it handle this click. That's just another type of event, okay? So if I go to the circle in person, and now you'll notice there's a thing called onClick, eh? And here I can get information about where I'm clicking and so on. All I want to do is infect this person. How do I infect this person? Yeah, I send a message. I could send a message to myself, or I could send a message directly to the state chart. In this case, I'll just send a message to myself. So I'll send this. I'll send a message infection to this. In other words, to myself. Eh? And I'll put a semicolon because it's a statement. it does something. It's not computing a value, it's doing something. So send, and this is the message I'm sending to myself. Does that make sense? Oh, let me put that up on the big screen. There we go. Where am I putting that? I'm putting that in the onClick handler for the oval under the dynamic properties. Does that make sense? Okay, should we look to see if it works? Okay, so let's go work. Let's go compute. Okay, so here we go. So now we should be able to click on something. Oh, look at that. I just caused a little outbreak. Boom. Now it's starting to spread. Boom. Okay, look at that. It's spreading. Isn't that neat? That was a less than overwhelming reply, but the answer is yes, it's neat. Some questions are rhetorical. Okay, I don't know. I think that's kind of nifty. We could actually start to use this to sculpt the network, right? We could use it so when we click on a connection, we could have the connection disappear, for example. We could do all sorts of things, but we don't have time. But it's an indication of just how powerful the interactive nature of this is. We have this option to handle user interface events like clicking and have the simulation respond to that. Alternatively, when we click on it, it could put up some information or print out some information about individual history, so we could kind of go in and browse around. Okay, any questions to that before I think we'll go on to a case study? Questions? So we now have infection transmission of the sort we've built it up from scratch. Questions? Yes. That's a good question. It's certainly covered in the videos, and I'm not certain if it's in the notes. Yeah, I'm not certain. It's in for my MIT lectures. It's either where I covered messaging or I covered events. I think I have a little video, but it just does this, and of course I'll be posting this, so you'll get to see that. Okay, question. Yes. Indeed. Sure. Sure. Actually, that's a great segue. So, and I think in the interest of time, I'm going to actually take advantage of that to eliminate a sort of substantive line of discussion. So in my notes, I have quite detailed discussion on the many network types, some of their characteristics, some of their properties in terms of distributions associated with them. For example, the scale-free network power law distribution in terms of degree of individuals. I would recommend people go look at that, but I'll just show some the different network types. Okay, so we have a distance-based network here. So there's two semi-orthogonal things here. And I should really to be better prepared for this, I should or to keep my remarks clear, I should really go and open up this. So the deal here is that in AnyLogic, the environment defines spatial and network context. Okay, and we've seen that for space, and we've seen that for network type with distance based. Here, the two are coupled in principle in the sense that you have network topologies, spatial layouts, but there are some of each that will imply things about the other. So there's some coupling between them for certain types of networks. For example, a distance-based network depends on people's position. For a certain type of layout, a spring mass layout, it determines the position based on network connectivity. So there's some coupling here, okay? So there's distinct node attributes: location, connection. To whom are you connected? Where are you located in space? Okay, those are two distinct things. Spatial layouts determine where nodes appear in space, but also the logical position of them, as Robin was asking about earlier. A network type determines who is connected with whom, who is connected to whom. And for the most part, these characteristics are determined independently. Network topologies can be defined either alternative to or addition to spatial layout. So we have these sets of different networks that are provided. We have a set of different layouts. So networks we have, and we can go there, and it's just wonderfully flexible. We have a user-defined network. We can set up all the network ourselves. We can read it in from a file. I have example I've given to you where I do that from several types of different files. We could have it change dynamically, etc. We could have a random network. This is known as a Poisson random network, or Bernoulli network, for those familiar with that terminology. We have a ring lattice network, which is where each person is arranged logically. They're connected to neighbors only. Okay, so it's the most local type of network. We have a small world network, where people are mostly connected to neighbors, but a few of their connections are with people in arbitrary other areas of the network, with randomly chosen people. Okay, so most are local, a few global. We have a scale-free network, which is associated with pronounced power law distributed differences, distribution associated with degrees. So some people have very few people have tons of connections, but most people have quite few connections. Okay. And then we have a distance network that we've been seeing. So you asked about those network types. There's a set of layout types that accompany them. And these layout types place someone's spatial location, sometimes taking into account aspects of the network. So, for example, randomly located. They can be arranged in a grid, for example, as was that example we ran with this morning with the sort of spread. They're arranged in a grid. It could be a ring. They could be located in a ring in space, even if they're not connected purely with others in a ring type of way. This is about spatial layout now. A spring mass, so here we adjust node locations, so where they are logically, such that those who are close together in a network get placed close together, and then a user-defined one where the user can define the networks. Okay, and I note that for the distance-based network, there's this coupling between what's primal there is the location, and the network is defined from that. By contrast, if you have a network that's spring mass, what's primal is your network, and then you are placed based on that. So distance-based, we talked about. Ring lattice is purely local connectivity. So we'll just run this with many of these. So if we do let's do a ring lattice network, and let's lay it out. Well, here, let's not lay it out first in a ring lattice. Just run it. And what you will see is a situation where the entire network is connected, but it's puzzling. What's connected with what? You can't really see structure to it. But if we lay it out using the appropriate layout algorithm, here, click on the environment, and we want to set the layout type to be ring, then we can run it, and then we will see individuals arranged in a ring. Each individual is connected only with neighboring individuals. There's a big implication of that. You'll notice the infection spreads, but it spreads very locally. It's confined to spread in sort of a one-dimensional space. And so, to get to someone two over, it has to go through the next person. So there's all these kind of firewalls that will, that's a distortion, but there's it has to go in a very linear way. And so it tends to spread very, very slowly. Does that make sense? By contrast, we could keep this ring lattice layout, but we could make use of, for example, a connectivity. So there's layout, which is associated with location, but we can make use of a connectivity, an underlying network that's, say, random. Okay, we just displayed a ring lattice network. You're connected with neighbors, and it could be one neighbor on each side, two neighbors on each side. we're going to now display a random network, a Poisson random network in a ring layout, okay? So here we'll have people arranged in a ring. It's just they're connected with people all across the globe. See that? By contrast, a sort of intermediate, ladies and gentlemen, between those two, is a small world network. Small world network is sort of part ring lattice, part Poisson random. Maybe it's 90% ring lattice, 10% Poisson random. Ladies and gentlemen, let us do that. So let's choose now a network type that's a small world network. And I have slides on all this that I don't have time to go through. Here's the small worlds is here it is. Small worlds is a weighted combination of these two: ring lattice on the one hand and random network. And the neighbor link fraction, which Mike was asking about before, it dictates what fraction of the connections are just from ring lattice and what fraction are global. So here we're going to have a neighborhood link fraction, say, of 95%, and a connections per agent, say, of 20. Okay, so each agent will have 20 connections. 95% of those will be local. What do you expect this network will look like when I draw it? 95% of the connections are local. They're with my neighbors, my nearest neighbors. 5% are global. What would that look like? Sorry? So it looks something like this. So people, by the way, their sizes are still being determined by the number of connections, so they're kind of fat. But you'll notice that most people are connected locally, but there are these occasional connections across it. Some are rewired to go across it. Okay. And then we have a scale-free network, which exhibits the sort of power law scaling you see. And this is from Schneeberger's work on scale-free networks for sexually transmitted infection. Again, this is the case where often the tail can wag the dog. You have small numbers of individuals with tons and tons of sexual connections per year, and then number of sexual partners, and then most with few. And in this case, you have this sort of power law relationship with your chance of having k connections goes down as k to the minus some gamma, and it's been observed in several populations. And here we'll get a preponderance of nodes that have low number of connections and some with very high. Okay, so that's a scale-free network. Each of these will have different sort of parameters that it needs, some overlap, but we'll have different parameters required for different networks. So we could have, for example, a scale-free network, and then there's this M parameter, and we saw a distance-based connection. So does that address your question? Okay, so I refer you to this network lecture, which I'm now not going to be giving. There, we will talk about dynamic networks and see a little bit how that goes. But I'll leave the issue of sort of network structures for you to review. So I have done lecture 20, but I'm not sure if that's consistent with the version that you have. I think it's called networks. 18. Thank you very much. Yeah. So there's a whole bunch of things in the network types, giving illustrations and talking about the meanings of the parameters, and giving some warnings at the end on interpretation, etc. Bear in mind that these networks are very handy to use up front, but you can make them dynamic. These are some descriptions of how we make them dynamic. We can connect agent A to agent B. We can disconnect the two of them, saying A, disconnect from B. And we can ask, we already saw this, get connections number. We can ask if two are connected. We can get connected agent. We actually use that with it when we're connecting up people visually. And we can ask for all the connections associated with an agent. So there's a set of methods that you can use to get required information associated with a given agent. Okay. Okay. So those are all my comments that I'm going to offer right now on that front. We'll revisit the dynamic network issue a little bit later when we look at events. Okay. Okay. Any questions before I go on to a little case study? Okay. So Jeff, is it okay if I do a case study? Okay. So I'm going to offer a little case study that is related to our work in TB, and I'll see if I can use this to shed light a little bit on some of the trade-offs between different modeling methodologies and some of the reasons you might prefer one to another for a particular purpose, bearing in mind that in many cases they're best used together. Okay. So just looking at this to make sure I don't already. Right. Okay. So pardon me, I have another version of this for this boot camp specifically. Okay. So I recently gave a little update to our Public Health Agency of Canada, and I just wanted to use some slides from there in the interest of expediency. So this is all work that I do with a variety of collaborators. I'm gonna stop this and